Okay, so we're going to look at the normal distribution and what that means in terms of a data set. So the normal distribution, like normally distributed data, like it's all about data, and the data is special because in it, in the center, you have the mean, the mode, and the median all being the same. So they're just your normal, things from statistics. So if you've got a set of data and these three things are the same, then the data is normally distributed. And lots of things like this that exist in the world, like people's IQs is a good one. Like IQ is not a great example in terms of, what it actually means, but the IQ test was designed in a way that it would be normally distributed. You would have very few people up in the extremely high IQ range, and you would have very few people down in the extremely low IQ range, and most people, in this chunk here, which is where most people live in the IQ. So things like IQ are, people's heights is kind of normally distributed. Lots of tests that we do at school end up this way. We standardise the data and manipulate it so it ends up looking something like this. And you can do that through like different means. But the IQ one is the one I'll talk about most. So IQ, the average person's IQ is supposedly 100 based on IQ tests that have been created. So that means that if the data is all symmetrical and all nice and neat and the mean, mode and median are all the same, then that center point there would be 100. And as we move out from that point, so they break it up into chunks, which are standard deviations. And so they say the standard deviation of the IQ is 15. So that means that this point here is 115 and this point here is 85. So most people, the majority of people are within this range here, and it's a certain percentage. The way normal distribution works is that this in between one standard deviation, so one standard deviation above and one standard deviation below, there's 68% of people. So no matter what we're talking about IQ, we're talking about test at school, we're talking about people's heights, people's weights, whatever it happens to be, 68% of people lie within that first standard deviation range. Mm-hmm. Okay, and then we have another standard deviation which goes out to 2 and -2 and 3 and -3. And after that, it's so small as a percentage, we don't worry about talking about it. Now, this information is on your formula sheet. It's not in this form. It's just written as a list, and we'll talk about that in a sec. But you can take that list and you can draw your own picture and put that in. Okay, so this is the percentages, and it's broken up. So this section here, which is what we were just talking about with the IQ, 34 and 34 make 68. So that part there is 68. Now, on your formula sheet, it doesn't give you all this little breakdown. It gives you between -1 and 1 is our 68%. And then it says between -2 and 2 is 95%. Mm-hmm. So that means that 95% of people, so almost everybody, is between those two little bits. And then lastly, the third standard deviation, like this is virtually everybody. Like the green is 99.7%. So anyone that's outside that, this bit here and this bit here, like these are, you would consider them extreme cases. So if we're talking about IQ, if each section was 15, we would have, this would be 15, 30, 45. So these people have an IQ of more than 145, which is like Stephen Hawking, Einstein, like extreme cases. And these, like on the other end of the spectrum, like these people down here, would have difficulty functioning by themselves. So talking severe mental disability in terms of capacity and to function. So your formula sheet doesn't break it up quite so nice. It just gives you those three big numbers of 68, 95 and 99.7. But I mean, you can remember the other numbers, but there are a lot of numbers to remember. But if you can work out, if it's 68 for the first one and it's 95 for the second one, then 95 minus 68 divided by 2 will get you 13.5 and 13.5.
Yep.
Okay, and then you can do the same thing for the 2.35, and then the last bit. Well, the last bit is whatever's left over, which is 0.3 divided by 2. All right, and the Z-scores themselves. So these, 1, 2, 3, 4, all of these, they are Z-scores. They are standard deviations. So a standard deviation of 1 is it means one standard deviation above, but they can also refer to them as Z-scores. And a Z-score is like a standard deviation, but it doesn't just work on whole numbers. So you could have a Z-score of 1.3 and of minus 2.5. Like you can have all different in-betweens. Yeah. And we don't work with the percentages with those, but we use those to compare. So we could compare, say, an English result to a maths result, even though they're totally different. If we worked out what the average and the standard deviation was in your English test versus the standard deviation and the average in your maths test, if you had a higher Z-score, you would have done better compared to the people that did the same test. It's not all just based, like if you got 90, that's better. If you got 90 and the average was 95, then obviously you didn't do as well. If the average was 50 and you got 51, it all comes down to comparing what the test was like. Okay, so if you want to calculate a Z-score, which is on your formula sheet, we use the formula Z equals the score minus the mean divided by the standard deviation. So let's say in your maths test you got a score of 90 and the average was 75 and the standard deviation was 12. Okay, we could work out your Z-score. So 90 minus 75 is 15, so 15 over 12, which is 1.25. And that Z-score we could then use to compare to a different test where you had different results. So if that was your maths result, we could do your English result, and if your English result was 2.1, but you only scored, so let's say in English you scored 57, it was a really hard test, and someone asked, did you do better on English or maths? And you said, well, I got 90% in maths and I got 57% in English, and people would say, well, obviously you did better in maths, but based on the Z-score, your Z-score in maths was only 1.25, whereas this 2.1 result in English, you did heaps better than everybody else. So that would put you outside that 95%. You would have beat more than 95% of people with a Z-score of that. This one, you're beating the middle section and the bottom. Yep. But the other guy, the English guy, you're beating most people because you're pretty far outside the mean. So the classic test questions are calculate the result, compare the results. Yep. And you do that by just getting the Z-score. Doesn't matter what they actually got, it just matters what their Z-score comes out as. The backwards ones is where they're going to give you, say, Johnny got a Z-score of 2.5. on his last test. The average was 71, and the standard deviation was 12. Okay, and so they'll say calculate Johnny's score. What was his score? What did he actually get? So if we use the formula, Z-score equals the score minus the mean divided by the standard deviation, we've got enough information here to work it out. We've got 3 numbers and a variable. So we say the Z-score is 2.5 equals X, because we don't know what he got, take away the mean, divided by the standard deviation.
Yep.
All right, and then this is just an equation, same as it is in algebra. We multiply the 12 up to the 2.5.
Yep.
So 12 times 2.5, of course it is, it's 30, minus 71. So Johnny got 101. Okay?
Yeah.
So obviously this is not a percentage question because you can't have 101%, but so the test might have been out of 120, or it could have been out of anything.
Yeah.
But the process is the thing that matters, and it's either they'll leave out the score, or they'll leave out the mean, or they'll leave out one of them, and then you've got to solve it in pretty much exactly the same way.
Yeah.
And that is basically the other type of question. So the first one is figure out the Z-scores, compare the results. The other one is work out what they should have got or what they did get. So, and that it's basic. It's an algebra question then.
Yeah.
The Z-score formula is on the formula sheet. Plug in what you know, solve it. So once they've talked about Z-scores, in the test they can ask you about the percentages between Z-scores or between standard deviations. It's not normally between the Z-scores. It's just the 1, 2, 3 and minus 1, 2, minus 1, minus 2, minus 3. So to calculate the percentages, it all comes back to your bell curve that we drew at the start. And if you start by putting the middle in, and on your formula sheet you've got the magic numbers 68, 95, 99.7. So if the first standard deviation, 1 and 1, is 68%, then half of that is 34 and 34. If we go to 2 standard deviations, then with the difference between 95 and 68, so 95 minus 68 is 27, and because these two sections are the same, we divide it by 2 and we get 13.5. So this bit here is 13.5, and this bit here is 13.5. And if we go to 3, then the difference between the last two, so 99.7 minus 95, gives us 4.7, divided by 2 is 2.35. So this bit here, 2.35, and 2.35, and the last bit is 100 minus 99.7 is 0.3, and then half of that is 0.15. So then you can answer any question they ask. So if they say, what is the percentage of people between a Z-score or a standard deviation of 0 and 2, well, that's all these guys here, which includes half of the 68 and a little bit of the yellow. So we just add those two percentages together. So 34 and 13 makes 47.5%. So they can then ask you questions. They said if there are 100 people or 200 people in the data set, if 47.5% of them were between 0 and 2 standard deviations, we could work out exactly how many people that is.
Yeah.
By just doing basic percentage, 47.5 times 200 or, however many
Yeah.
things it is in the data set. So it all comes back to the normal distribution shape, the bell curve, and the questions, like they can be just general questions about particular standard deviations, 1, 2, 3, -1, -2, -3, or they could give you specific information. So if we talk about, the packet of tea, say, the mean grammage in a packet of tea is 200 grams, and the standard deviation is 10. If they tell us that the packets are normally distributed, so they follow this pattern, the mean is the same, the mode is the same, and the median is the same, then that means our centre line is 200, because that's our mean. Okay, that's also our Z-score of 0, or our mean of 0. And then if we go one standard deviation above, well, if the standard deviation is 10, then one standard deviation above is 210, which is one standard deviation. If we come one standard deviation below, then same idea, 190, and that pattern continues, 220, etc., and then 180, etc. that way, and then they can ask percentage questions based on that. They could say what is the percentage of tea packets that are between a standard deviation of 0 and a standard deviation. What percentage of packets had a mass between 180 grams and 200 grams? And we would say, well, we know now that's 34, and this is 13.5, and so together, 47.5% of their packets of tea are between 200 grams and 180 grams. And then if they said, all right, well, we have 1,500 packets going out, how many customers are going to be disappointed because they've got less than average tea in their packets? So we would just do 1,500 times 47.5%, and that would tell us exactly how many packets of tea there are in that range. So that's 712.5 packets.